Imagine standing on a station platform, watching a train speed by at 100 miles an hour. If a passenger on board throws a baseball forward at 50 miles an hour, you don't see a 50-mile-an-hour pitch, you see a 150-mile-an-hour blur. The speeds simply add together. Physicists call this intuitive rule the Galilean transformation. It rests on the assumption that a yardstick is always exactly 3 feet long, and a second ticks at the exact same rate, whether you are standing still or hurtling down a set of train tracks. But what happens if you swap that baseball for a flashlight? If the train is moving forward, the beam of light should logically get a boost. A ground observer should see the light traveling at its normal speed, plus the speed of the train. In 1887, physicists Albert Michelson and Edward Morley built an incredibly sensitive optical device to measure this effect. Instead of a train, they used the Earth itself, which travels through space at 67,000 miles per hour. They expected to see light beams shift speeds depending on whether they were fired with or against the invisible ether they believed filled the universe. The experiment returned a 0 result. Light fired forward moved at exactly 186,000 miles per second. Light fired backward moved at 186,000 miles per second. The math from the train platform completely failed. The speed of light refused to change, no matter how fast the source was moving. This broke classical physics. The universe has a strict speed limit, and to enforce that limit, our intuitive understanding of space and time had to give way. Enter the Dutch physicist Hendrik Lorentz. He sought to save the classical laws of physics from the wreckage of the Michelson-Morley experiment. Lorentz proposed a physical explanation for why the light seemed to travel at a constant speed. He argued that, as an object pushes against the ether of space, the physical material of that object actually contracts in the direction of motion. He developed a set of equations to back this up, calculating exactly how much an object would shrink. As velocity approaches the speed of light, the length of the moving object contracts. Lorentz thought this was a mechanical pressure problem. He believed the forces inside an electron were being physically deformed by the friction of moving through the ether. His math perfectly erased the error in the measurements, yet it relied on a mechanical explanation that didn't exist in reality. He had found a mathematically flawless equation without knowing what it actually described. In 1905, a 26-year-old patent clerk named Albert Einstein looked at Lorentz's math and stripped away the physical ghost. Einstein realized the ether wasn't necessary at all. He built a new framework on just 2 rules. The laws of physics are identical for any observer moving at a steady speed, and the speed of light is a constant for everyone, everywhere. This diagram illustrates the result. A rod measured by a stationary ground observer is L0. The rod measured by a passenger in a moving car is L'. They measure different lengths because they view the same object through different space and time coordinates. But Lorentz's mechanical pressure was an illusion. In Einstein's view, the rod remains unchanged. It is the grid of space and time itself that is oriented differently for each observer. To reconcile these 2 distinct realities, physicists use the Lorentz transformation. It acts as a mathematical translation dictionary, converting the coordinates of an event from a stationary frame of reference into a moving one. If the speed of light is the universe's unmoving anchor, everything else has to flex, space itself contracts, and time itself dilates. The Lorentz equations provide the exact scale of that universal distortion. A few years later, mathematicians noticed something striking. While length and time changed for different observers, a specific combination of both remained constant for everyone. This kind of mathematical invariance is the signature of a rotation, not in 3D space, but in a 4-dimensional manifold of space and time. Think of how a solid 3-dimensional object casts a different 2-dimensional shadow depending on how you rotate it. In a similar way, this hyperbolic rotation tilts your coordinates. As you accelerate, the way your reality projects onto the axes of space and time shifts. This is why 2 people disagree on the length of a car or the ticking rate of a clock. Neither person is wrong. They are simply viewing different geometric projections of the exact same event. But underneath those shifting measurements, there is a fixed reality. By plugging space and time into the Lorentz transformation, you calculate the invariant space-time interval, a single 4-dimensional distance that all observers agree on, regardless of their speed. In this 4-dimensional reality, increasing your speed is equivalent to turning your perspective. You are tilting your path through the fabric of the universe.